phone. All right, so we're on 6.9 now. 6.9, ready?
Yeah.
All right, it says here. Back to 6.7. What? We just did 6. Okay, hold on a second. The equation the velocity equation we have is v of t equals negative 9.8 t plus 20, right?
Yeah.
What if I asked you for the acceleration?
Negative 9.8.
It would be take the derivative. Take the derivative. That falls off, right? That one falls off. And then over here I have the raised to the power by 1. So then throw the thing out front, get negative 9.8, right? Agreed?
Yeah.
All right, good deal. What's the acceleration at 2 seconds, by the way? Just for the record. Negative 9.8. There's no place to put a t. It's constant. So far, so good? Okay, now for this fix something completely different. What if let's say you throw a rock up in the air, so the acceleration is equal to negative 9.8. What would be its velocity?
At 2 seconds?
At 2 seconds. So how do I find velocity? We would integrate, right?
Seconds, acceleration decreases. If you throw a rock into there, gravity's going to affect the acceleration.
No. Acceleration is the same as you throw a rock up in the air.
Oh, yeah, never mind. Yeah,
but that's a physics concept. In math, we just assume it to be true and not worry about those little details. dt, right? Be with me here, because this is huge. We're having that moment where you're learning something brand new. It's the last brand new thing in this chapter. You with me?
Ooh, no. Yeah.
Okay. So I'm going to integrate this, and what do I get? Hummer, integrate it. Just look at it and integrate it.
All right, so it's going to be negative 9.8x.
Negative 9.8. We're going to use a t because it says t over there. So that's my a of t for any time t. Sorry, my v of t, right?
Yeah. And
so my velocity, according to you, would be negative 9.8 times 2, which would be negative 19.6. Agree with that?
Sure.
Yeah, we got that?
Yeah.
It's wrong.
What?
We know it's wrong.
Yeah.
What was our initial velocity? If I plugged in 0, I get 20. What happened to my 20? If I plug in 2, I should get negative, or should I get 0.4 like we did in the previous worksheet? What am I 0.4? It's gone. We broke it. So what's the problem? The problem is this. Are you ready? This is a rate. Agreed? It's a rate at which something's happening. Does the rate tell you where you start? Let me ask you a following question, Ms. Leonce. Are you ready for it?
Sure.
I'm driving to Los Angeles. I drive at 55 miles an hour the whole entire time there. On my way there. How long does it take me to get there? There's no way to know how long it's going to take because I don't know where I started. Rate information does not tell you how much water's in the tub before you turn it on. It tells you how much water you can put in the tub, but it can't tell you how much water started in the tub, right? So we're missing what we're going to call the initial conditions. How much water is in the tub? How fast was I going at the beginning? That's what I'm missing. I'm missing how fast I'm going at the beginning. So I can't tell you how fast I'm going at the end because I know it changed. It went down 19.6. But how much did it start with? I don't know. And so every integral problem we've done thus far is wrong. What? You just made me do a whole worksheet of wrong problems. Yes, I did. Because when we do an integral, from here on out, we're going to add a plus c. And unless I tell you what the initial conditions are, that stays plus c because I don't know what they are. Which means, on the previous worksheet, this is plus c. 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 They were all wrong. Every last one of them wrong. Because there might be an initial amount of water in the tub. We can't control that. Knowing how fast something's going doesn't tell us where we started. It can't. Knowing how much water we're putting in a tub does not tell us how much water's in the tub unless we know how much water was in the tub at some point. Right? We can't answer that question. Right? How long is it going to take to drain the pool? How much water was in the pool? I mean, I can see how much is coming out of the hose, but I have to know how much is in the pool to begin with, don't I? This is what we're missing. Does that make sense?
Yeah.
Okay. So whenever we do an integral, we tack on a plus c. Got it?
Got it.
Got it. All right. So let's look at the back of 6.9. Back of 6.9. An evergreen nursery usually sells a certain shrub for 6 years of growth and shaping. After 6 years of growth and shaping. The growth rate of these during these years is dHdt is equal to 1.5t plus 5, where t is in years and h is height in centimeters. These shrubs are planted. These shrubs are planted when they are 12 centimeters tall. Find their height after t years. All right, so here's how we're going to do this problem. Are you ready?
Let's draw with that.
I have dHdt. That's the rate at which the tree is growing, correct? Correctamundo?
Yes.
Okay. So how do I find how tall the tree is? That's the rate. How do I get to how tall? Mr. Fleming, how do I get to how tall? Integral. So h would be equal to the integral of 1.5t plus 5 with respect to time.
So are you doing an S when you do that?
It is a super big S that looks like this. It's a flat S that looks like this. It's called an integral sign. It's a summation sign as well, but we don't worry about that. Just make it a super big, relatively flat S, and you're good to go. Okay. All right. So, how do I do this, Mr. Fleming?
So 1.5
Over 2 plus
5
plus C. Don't forget the plus C. If you Google plus C, don't forget the plus C, you will find various calculus classes singing songs that say don't forget the C. Because the C is going to get forgotten. You need to remember the C. That's your job. Yes?
Well, for this one, we're given a 12, but we had a plus 12, so plus.
That's the next thing we're going to do. Now, the next thing we look for is, do we have the initial conditions or any conditions? If I have conditions, I can figure out what C has to be, right? So what they're telling us, at time equals 0, my height is what, Mr. Leoncio? 12. So if I plug in a 0, now, this is the official way to do it that we'll talk about, generally speaking, what you do. H equals, if I plug in a 0, that becomes 0, that becomes 0. C, so the H should be 12 when the time is 0. So what must C be? 12. And so H equals 0.75 t squared plus 5t plus 12. Now, Ms. Leoncio's instincts are good because he said, don't I just plug a 12 in there? The answer is 90% of the time, the answer is yes. The only risk you run is this. If I give you at time equals 2, it's 25. Then I need to plug a 2 in here and a 25 to figure what C is at the initial conditions. There's one other risk. If I give you at time equals 2, it's sitting at 12, it's a height of 12. That means I need to plug a 2 in here for time. Because at 2, it should be 12. And that would tell me what C is at the initial condition, at the initial moment, right?
So you plug in T, do all
If I said at 2 years, the height of the tree should be 25.
Okay.
I would plug in 2, 25, and that would tell me what C has to be.
How would you know it's 25?
Because I told you, if I tell you at year equals 2, it's at 25, then you'd have to plug in 2, 25 to figure out what C would have to be, right? So that's one way which this can confuse you. The second way in which you have to plug it in and worry about plugging it in is this, okay? The second way you have to plug it in is if you look at the problem and you go, if, for whatever reason, this doesn't give me 0, if I plug in 0, this gives me like 18, well, then my C can't be, my C's got to subtract 6 or something to make it 12, right? So sometimes that happens. That doesn't happen very often, but in real life things, but sometimes on calculus tests, they'll check you on that. Okay? So generally in theory, that the right way to do this is to plug in 0 and figure out what your C is.
Okay.
Generally speaking. If you picked up Leoncio's habit of just plugging it, just throwing it over there, you're 90% of the time going to be right. Because usually this amounts to 0, right? This middle section is going to amount to 0. Got it? Okay. How tall cheese when they're sold? Go ahead and figure that out. Try the next one. Try the certain bacteria is dp dt equals k square root of t. Initial size of the population is 500. After day 1, the population is 600. Estimate the population in 7 days. Try this one out and see how we do.
What is K?
They didn't give you t, did they? But it's some number, right? K is a number, right? So you're gonna try. You have to figure out what k is based on the information. All right, so that's my population. I want to know how many bugs I have, so I'm going to take the integral of this, right? So my population would be equal to the integral of k t to the 1/2 power dt. So that's going to be, the k doesn't matter because it's a number, right? So I'm just going to pull that out. I get t to the 3/2 divided by the power I get. So raise the power by 1, divided by the power I get. So I put 2/3 out in front, plus c, because now we remember our plus c, is equal to our population.
Oh, I did it wrong. I thought K was the C.
K started as part of the rate, so you need a plus C at the end. So here we go. How am I going to find C and how am I going to find K? Because I still haven't found either one of them. So if I plug in my values, if I plug in 0 and 500, I get 500. It should happen when I put 2/3, don't know what K is, T is equal to 0, 3/2 plus C, right? Well, this whole middle section is going to become 0, isn't it?
Yeah.
So that goes away. So I get C is equal to 500 using Leoncio's rule of, isn't that the initial condition? There's 500 bugs. I should just make C plus 500. Works in this case. So here we go like this. So our population formula is now 2/3 k t to the 3/2 plus 500. Now, how am I going to find k? Put day 1 in now. I should have 600 bacteria on day 1. Right? Subtract the 500 across, I get 100 equals 2/3. 1 to the 3/2 is just 1, right? So this is K. So multiply both sides by 3/2 and I get 150 equals K. What? 6?
Oh, wait, never mind now.
Yeah.
Is that okay?
Yeah.
All right. So then my new population formula is 2/3 times 150 t to the 3/2 plus 500, right? And 2/3 of 150 is 300 over 3, which is 100. So my final population formula is going to look like this.
Now we plug 7.
And then I plug in 7 and I can find my actual amount of bacteria.
Yeah, we're freaking close.
And by the way, do we round to the nearest whole bacterium or do we go 3 past the decimal point? 3 past the decimal point. Unless I told you around the nearest bacterium, you don't do it. You go 3 past the decimal point. I don't care how silly that sounds. So 7 to the 1.5. Up. 7 to the 1.5 times 100 plus 500. I got 2352.
Yeah.
2352.026 bacteria.
Yeah. Oh.
What? 0.026. What? What are you saying?
Yeah, I got
I got one.
0.035?
I got 17,650.
0.03, but you got to go 3 past the decimal point.
I know, but it didn't like, it just gave it to me.
Okay,